Welcome to another CO2 Mondays with Trevor. I'm your host, Trevor Matthews, and today we got a great conversation happening. Returning guest, Andre Patenaude. How you doing, Andre?
I'm doing great, Trevor. How about you?
Oh man, I'm doing fantastic. It's a beautiful day here. Well, I think we should just get right into it. What do you think?
Yeah, yeah, for
So
sure.
I've been on social media. I'm on social media all the time, and I've been seeing lots of posts coming from you on this new transcritical booster lab in
Yep.
Sydney. Why don't you tell everyone about what's going on there?
Yeah, excited to talk about it, Trevor, because it's it's actually something I've been working on. I've been leading this project for the last couple of years. It's a uh, it's a really exciting project in that we wanted to be able to have a CO2 transcritical supermarket system that we could use to do all of our testing, validation, learning, anything you need a lab to do, right? So, and when we decided to build this lab, we wanted to make it appear like a supermarket. And I don't know if you saw the post just on the weekend. The big machine house got
Yeah.
delivered. So this is a 37,000 pound, you know, machine house with rack inside it. I was actually had to three trucks had to deliver this thing because it's an L shape. So what's really exciting about this is we've going to also have it's in the middle of our Sydney lab infrastructure. We've got 100,000 square feet of brand new
Wow.
labs in Sydney, Ohio, which is
Awesome.
part of that $100 million investment that Emerson's made. So we've carved out 2,500 square foot supermarket area. We're going to have 18 display cases, and they're from 5 of the different case manufacturers in the US. We're going to have
Cool.
walk-in box, walk-in freezer, and this system's going to be 360,000 BTUs medium temp, 120,000 low temp. We're going to have complete capability to run off false loads
Oh,
or actual DX case loads or combination thereof. I don't know if you noticed a month ago, we showed pictures of the gas coolers being dropped on the roof.
yeah, yeah. I
So
see
we
those.
have a dry gas cooler. We also have an adiabatic gas cooler. Plus, we've got a water-cooled gas cooler that runs off a chiller. So we can control the outlet gas temperature any time of year, whatever we want, if we use the water-cooled condenser gas cooler, which is really cool.
Yeah.
We could, like I said, we could change the false loads to what we want. We've got enough room on the rack that it has 3 medium temp compressors today, but we can add 2 more if we wanted to put smaller compressors. We have parallel compressors. We have 2 parallel compressors because we want to understand how low can we go using parallel compression by making your compressors even smaller and trying to run with a little bit of flash gas coming off that flash tank. That's
Yeah.
another thing we did. We added 2 suction groups, one satellite low temp plus the normal suction group low temp. And both of them have independent liquid line subcoolers as well. So we can understand all of those system dynamics. We've got a low pressure receiver or accumulator. So we'll be able to run liquid ejectors. We'll be able to run high pressure ejectors. We'll be able to run, of course, parallel compression, adiabatic gas cooling. We've got a mechanical subcooling loop. We've got a heat reclaim. We'll be heating the supermarket with discharge gas with the heat reclaim. So there's a lot of stuff that's in this system. So we could test whatever we want. We can work with our OEM customers on strategies specifically for CO2 or even end users that are interested in a specific application or an ambient condition that they'd like to be able to reproduce. And we can do that here. So we're going to have a dedicated staff, of course, at the center to be able to do that. We expect to be up and running by the end of the summer. So
Wow.
we're starting to do all our baseline testing by the end of the summer, and we're working through all that, of course, to make sure that we have all that done.
Awesome. Yeah, no, that sounds Super cool. Are you going to, is this going to be just a lab for testing, but are you going to have like people coming in for training at these facilities to like technicians and contractors, or will this just be for OEMs and end users?
Well, it's going to be for that specifically as a lab. So a lab environment is not so much a testing, it's not a training environment.
Hmm.
However, when we're working on collaborative projects with OEMs or end users, of course, we'll be working within this space
Yeah.
and doing whatever we need to do. So that's one piece. We did purchase, as you know quite well, a CO2 transcritical mobile training unit
Hmm.
that you've trained on that. The US have one now, and its home base will be Sydney, Ohio.
Okay.
So we've already done some training there. We'll continue to do training using that mobile trainer. And of course, it's a mobile trainer, so we put it on a trailer and send it
Yeah.
off to whatever part of the US that we need to in order to run hands-on CO2 training. So we'll have that
Yeah.
option as well.
Yeah, no, that's super awesome. And this facility is gonna, it sounds pretty awesome. I can't wait to get an invite to see it when it's up and running. That's gonna be pretty exciting.
Absolutely.
So today we're gonna be talking about CO2 compressors and diving into Copeland CO2 compressors because you guys have a lot. You know, you have a lot going on, and I'd love to start with the semi-hermetics, the transcritical or the medium temp ones, and find out some of the differences. So find out, you know, what are some of the differences between just say a four-cylinder HFC Copeland and a transcritical Copeland? What are maybe some of the physical differences?
Sure. Let me bring up maybe just a slide to kind of bring up the system.
Yeah,
If I could share that one slide with us, kind of a
please do.
typical. Can you see that? Okay.
No, you're not sharing right yet.
I am not sharing right yet. Okay. I should hit the share button. Okay.
So yeah,
How
so
about how's
there
that?
you go. Yep.
Okay. So one thing. So you talk about differences within an HFC to a CO2 system. One main difference is the fact that the pressures are significantly higher with a CO2 system than it is with an HFC system. So the resiliency of that body must be much greater. For example, the 4 MTLS medium temp compressors we have there were burst tested to 10,000 pounds. So
Wow.
you can imagine the thickness of the cell. Not only that, when you look at the end bell, all of the bolts, there's like over 20 bolts on that belt,
Wow.
that end of the compressor. So a major difference, of course, is that. The other major difference is the size of the pistons. Now, you take an equivalent HFC compressor, 404A, will have a much larger diameter piston than a CO2. You look at a 150,000 BTU compressor is really small piston diameter relative to an HFC, which looks twice the size for the same capacity.
Wow.
But don't get fooled, the motor is the same power to move that refrigerant, but the diameter of the pistons are smaller. That's one thing. But when you look at the wrist pin area, it's larger
Yeah.
because the forces are greater.
Yeah.
So it's kind of bizarre when you look at that wrist pin on that piston. It's a smaller diameter, it's a larger diameter pin so that you've got more surface area because of the greater forces. So that's also important. The reeds are not discus type reeds. They're conventional reeds instead of a discus puck because of the pressures, once again, that CO2 has. The design needs to go to that reed type development or design. So that's another thing. The other thing you'll find on the transcritical medium temp compressors are 2 pressure relief valves.
Mm.
Now, for UL requirement, you have to have a discharge valve. And that pressure relief valve on the discharge side of a medium temp transcritical compressor is around 100, ours is 135 bar. 135 bar is close to 1,900 pounds, 1,800 and plus pounds. So to give you an idea, that's pretty high. Now, there's also a low side pressure relief that's not required by UL, but it's 90 bar if someone wants to put one on. But it's not a UL requirement. So a little bit different there. From a CoreSense Protection module, on the front of the compressor, we have this device, which is a CoreSense Protection module. It protects the compressor against a number of failure modes that can occur. And one of the differences between the discus version and the CO2 version is it already has installed a high discharge temperature sensor. On the discus version, you have to add it yourself and plug it into the control module.
Yeah.
On the CO2, it comes pre-installed, pre-wired, ready to go.
Yeah.
So, and the other thing that's kind of unique as well is the footprint on our 40,000 BTU model is the same lay-in footprint, not the lay-in, the footprint, as our large 50 horse.
Wow.
So that's a little bit different, but it's about pressure resiliency and safeties around it. That are the main differences, of course.
Yeah. And I did notice when I've tore a few of them apart that they don't have a pump on them. Like this, I guess the smaller size. What can you talk about that? I think they got a slinger feed or a flinger feed that they
Yeah,
call it.
absolutely. So when you walk up to one of our compressors, if it's a 40,000 BTU all the way up to 150,000 BTU, which is called the 15ME, 4MTLS, 15ME. The 15 stands for 15 and M times 10,000, so 150,000 nominal. So 150,000 and below, there's 3 sight glasses on these compressors. 2 at the bottom where you would expect on each side of the compressor, which gives you flexibility to put your oil control on one side or the other. The other one, you might be able to see it on the slide. It's kind of hard to see, but it's right on the middle of the body of the bell, if you will.
Yeah.
Okay. And there's another sight glass there because those models, 150,000 and below, have a flinger feed, like you mentioned. So as the oil sits in the bottom of the crankcase, it splashes around the motor end, splashes around. It gets collected in this cup near halfway up the compressor. It collects in the cup and through centrifugal force gets driven down the crankshaft and splashes up inside, up the con rods and where the lubrication is required. So that's for the models, like I said, 150 BTUs and below. The larger ones, they have a positive displacement oil pump because now we're talking about a longer crankshaft. And centrifugal force is not enough to move it all the way across and make sure that you get adequate pressures up into where it's required. So the 3 largest displacements that we have, we call them the 20, the 22, and the 28, have a positive displacement oil pump. And that is connected to the CoreSense, and CoreSense now can alert you if your oil pressure is not adequate.
Yeah, and I that's something that is so unutilized in both HFC and CO2. Maybe the CO2 is getting a bit better, but I've seen so many sites where none of the core sensors are wired back to the E2 or wired back to the facility management. So any technician out there that you're working on any Copeland compressors with a CoreSense protection, you should be wiring that back up so you get that information for you. Because if you're on call in the middle of the night, it's nice to see how many times that compressor started, what the temperature was running at, and that's what I love about CO2 because everything is electronic and you can see everything that's going on and you can make a better picture when you're troubleshooting.
Absolutely. Great point. And you're right. So many times they're not, especially on the HFC system, core sensors are not hooked up to the facility management system. So
Yeah.
well, you're right.
And so we have the transcritical compressors. Let's talk a bit about the uniqueness with CO2 now? Because I know we've talked about it before, but like when I look in the application engineering bulletin for this compressor, and I highly recommend getting out to the Emerson website or get the app, the application engineering bulletin app, and look up the
Yep.
R744 transcritical bulletin. It
Mhm.
says in there that you need specific superheats, and I'd love you to talk a little bit deep about that because I think that's very important for everyone to understand.
Well, that's a great point. When CO2 systems were starting to be introduced in North America, most technicians didn't realize, because we didn't do a good job of communicating it to the field, that the low temp compressors need a higher superheat than what you're used to. So on medium temp, it's okay. Medium temp, it's 20 degrees superheat coming back to those medium temp compressors. And that's kind of the number that HFC compressors are used to hearing for years and years. So if you thought 20 degrees was also good in the low temp, you were wrong, because the application engineering bulletins state, not only ours, everyone that makes a compressor for CO2 for low temp, you'll read in their application engineering bulletins, you need 36 degrees minimum superheat. And that's because of the oil, the solubility of the refrigerant in the oil. As it gets colder and the superheat gets lower, what ends up happening is you get too much refrigerant entrained in the oil. And when it gets into those bearings, it starts to accelerate wear. You've got to keep it warmer. You've got to keep that superheat up so that the oil can do its job, which you may think is counterintuitive, but that's exactly what happens with CO2. You need to keep that superheat up to protect those bearings and load surfaces. And low temp, it's 36 degree minimum. Medium temp, it's 20 degrees.
Yeah, so around 10K and 20K, give or take.
Yeah,
For,
you'll see in bulletins when they talk about K. So Kelvin is 10 Kelvin and 18 Kelvin.
18, 20 Kelvin. Just keep above those numbers at least a bit because the first time I've seen that, looking at it, okay, I got 20 degrees superheat. This is good. Nothing wrong with this, but those low temp compressors, their bearings are taking a punishment, and I've seen lots of pictures and many compressors that have failed because of that. I think liquid dilution is probably one of the largest failures for CO2 compressors out there.
Well, it certainly was initially when that was not understood.
Mm.
Compressors were returned back and we're going, what's going on, dude? We do an inspection and find out, well, lack of lubrication. Well, lack of lubrication, why? And I remember talking to a guy, he was saying, well, what's the big deal? They come out of defrost and run 0 degree superheat for a few minutes. It is a big deal because you'll be changing those compressors. So, and just to be clear, when we talked about K versus Fahrenheit, K is Kelvin, which is the differential, so which is equivalent to Celsius. So 10 K or 10 Celsius is equivalent to 18 degrees Fahrenheit.
Mm-hmm.
So it's 1.8 degree Fahrenheit per degree Kelvin when you do the conversion. So it's not a straight temperature convergence, it's a differential temperature that we're talking about. So let's make sure that we're clear when we're talking about that.
Yeah, thank you for clarifying that. It's very important for everyone to understand. And so we have semi-hermetics on the medium temp side for transcritical. Do you use any semi-hermetics on the low temp side as well, or can you?
Well, that's a great point, and let me go to that because a lot of people may not realize that. Let me just bring this a slide, and I'll talk to it because I know if you're in a podcast, then you can't see. So really, what I want to talk about is exactly that point. So we do have subcritical scrolls, of course, that have been used in CO2 for many years. It was first UL approved in 2009, the ZO Copeland ZO scroll. But the
Zed.
semi-hermetic Z, yeah, depends. I've been in
Zed.
the US a long time, you know. So it's Z for Canada and it's Z for the US. But so we also have semi-hermetic type of compressors. So the semi-hermetic 4MSL, they're called. They have the same embodiment as the transcritical compressor. They have the 135 bar discharge protection. But the motor is much smaller. The motor is developed for low temperature application. So that's one thing to note. And we currently have 3 4MSL optimized motors for low temp in North America. That does not mean that you can't use a larger displacement transcritical compressors in a low temp application. It just means that you're going to have a little bit more motor than you really need because compression ratios are lower. But from a displacement perspective, you could do that. You'll be sacrificing some efficiency, but in some cases, if you're looking for a lot of capacity and you need a larger pump, then that would be one option if an optimized motor is not available. So,
and what's good about that though is that that gives you an option because it always comes down to it. If you have a compressor that fails and you can't get one, there's a potential option that maybe the wholesaler will have that one or the supplier will have that specific compressor.
that's a great point.
So it's good to know that you can do that.
Right. And whether it's in the subcritical range or the transcritical range, they can operate with a drive from 25 hertz, most models 25 to 70 hertz. So you've got a capacity modulation, very wide capacity modulation range that you can have. Now, of course, if you're going to the ZO scroll, you can go all the way down to 10% with the digital versions. And that's kind of really nice if you have a small supermarket. They've got pull down curtains at night, the loads drop off to almost nothing, and you don't want a compressor banging on and off all night. So you've got digital that can manage that small capacity variation in those low load requirements.
Yeah. And it's important to understand that because there is a difference between using a digital compressor and a variable speed compressor. And what are the two? What is the? And you kind of touched on it, but what is when would you do a variable speed over that digital? Is it that low turn down rate?
That's one of the cases. With digital, you can get down to that 10% capacity, and typically with a variable speed, it's about 40% on the low end. And the other thing about variable speed, if you go too low, then you have an oil return issue, potential oil if it's by itself running at low speed for extended periods of time. A little bit different with digital. When it modulates, it's a pulse width modulated signal. So it's either pumping at 100% mass flow or it's not pumping at all. So it's like a PWM expansion valve. It's either open or not, but the motor's still turning, but it's not pumping. So within a 20-second period, you may say, I need 50% capacity. Say, okay, great. For 10 seconds, it'll pump at 100% mass flow. And for the next 10 seconds, the mass flow will stop, other than the inertia that keeps moving it through the system. So that's how digital works. Whereas, of course, variable speed is in fact there, varying the speed over time.
Yeah, perfect. And that's a great explanation of it. Does Copeland have digital semi-hermetics for CO2 or any plans to set them up with digital compressors?
We do not have a digital for semi-hermetic. It's variable speed only for our semi-hermetic product line. Yep.
Yeah. Okay, excellent. So why don't we get, you started talking about ZO and we talked about digital. Why don't we talk a bit about the uniqueness of the ZO compressor compared to a standard HFC compressor? What are some of the differences when we get into those compressors?
Well, the ZO actually for subcritical is very, very close to a 410A compressor
Yeah,
because the pressures are practically the same.
yeah,
The embodiment very similar to a 410A. Of course, the inside is different because of the displacement changes, because CO2 displacement, of course, like I just like the piston, the scroll sets would be smaller, relative to an HFC compressor. So that's a little bit different. But again, the motor to capacity ratio is the same, but the scroll sets will be smaller. The other thing as well is the ZO subcritical scroll comes with a pressure relief. So you have to put a pressure relief on the low side of the system because the medium temp will have one on the discharge end. So that's another unique feature of that. It does have a sight glass, an oil fill and drain, just like you would expect. And the ZOs come in fixed capacity or digital, and there's actually 3 different displacements of digital. So one at 100,000 BTUs, digital model, one at 58, and one at 34,000 BTUs. Those are the 3 displacements, I guess, that have digital, or models that have digital.
awesome. Okay, I got a good question because I get this question a lot. Can you, if you have a digital compressor, can you add a variable speed onto that compressor?
You have variable speed. It wouldn't be advisable because of, you already have some capacity modulation there. Because the actual scroll is not rated, VFD rated above 60 hertz. It's very close to around 60 hertz. If it was rated beyond, then you could go above that, but that's not what it's been developed for.
Hmm.
Yeah.
Yes. And so what for the ZO compressor, we talked about the semi-hermetics. The ZO, do they have to follow the same guidelines for the superheat as the semi-hermetics would?
Well, if it's a low temp application, the answer is yes. Whether it's a semi-hermetic and low temp, or whether it's the scroll and low temp, that makes no difference on what the superheat requirements would be, because solubility is solubility regardless. So it's 36 degrees Fahrenheit minimum, scroll
Yeah.
or semi-hermetic. Great question.
Yeah, and I've been noticing even some new refrigerants coming out where I read in the Emerson or the Copeland bulletins where they're looking for higher superheats or maintaining like 20 degrees superheat, like 513A for an example. Are you seeing more and more of this from these newer refrigerants that are coming out as well?
Um, haven't really. No,
No?
it's a normal requirement so
Okay.
far. CO2 is the different one from a
Yeah.
low temp perspective.
Yeah.
Yeah.
Awesome.
Now the HFCs or HFOs blends are pretty much the same as HFCs were. Yep.
So I notice on some of the 4MTLS, like especially the larger ones, it says you can go from 30 hertz to 70 hertz, and I guess the lower capacity ones go from 25 hertz to 70 hertz. What's the difference
Yeah.
between those 5 hertz? What could happen if you do not maintain what you guys recommend for
Yeah,
the baselines?
it has to do with more mass flow because these are refrigerant cooled compressors, right? So you need to have a certain amount of mass flow coming across the motor in order to cool them. So as you get into larger displacements, and there's a lot of there's a lot of dynamics around motor development and motor cooling and all of that revolves around it. And they all have an operating envelope that they have to work within in order to make sure that that motor is operating properly and doesn't stress outside its limit. And that's really what it boils down to.
Yeah.
It's about motor cooling.
Awesome. Yeah, and it makes sense because most compressors well, most compressors used to fail because of overheat, and I still think they probably do, compression
Yeah,
ratio and overheating. But a lot of
absolutely.
compressor manufacturers like Copeland have been doing a lot of research and development, adding the CoreSense diagnostics with that
Right.
head temperature probe in the head to really reduce that down, which is very, very important to do that and to help the technicians out with that.
You bring up a great point. Let me just get back to, because you talk about discharge temperatures being a major cause of compressor failure, which it
Yeah.
is. You've torn down many compressors and you've seen the
Yeah.
effects of high discharge temperatures or high compression ratios and all of that. Well, think about that. Low temp compressor never goes through that anymore on this particular booster architecture,
Mm,
because the compression ratio is 2-to-1,
yeah.
not 26-to-1,
Yeah.
like some of our ZF, HFC low temp compressors we have. Compression ratios can get up to 26-to-1.
Yeah.
No, this is 2-to-1. It's discharging into a +20 suction, medium temp. So there's no stress there. There's no heat. There's no high temperatures. So those low temp compressors, unless they're flooded, they're going to last a long time.
Yeah. Yeah.
Absolutely.
So I do a lot of research, and I do review and look up as many different compressors that Copeland does have. And I know in Europe they came out with a ZOV compressor. Can you talk about the difference between a ZO and a ZOV? And I even seen this on
Sure.
HFC models too, like ZPV. So you want to talk about that a little bit?
Sure. The V refers to variable speed.
Hmm.
So that's really what we're talking about. So when we're talking about a scroll product line and we add a V to it, it's because it's variable speed, and it's not an induction motor. It's a motor that's been specially developed for a wide range of modulation. So we talk about it's a BPM motor, wide range of modulation. So the ZOV that our European colleagues have launched a few months ago, not launched in the US. There's motor development that's required, but in Europe, they have it in 400 volts, 50 hertz. And that ZOV can go from 20 hertz to 100 hertz.
Wow.
So very wide range, number one. So that, and that's a CO2, low subcritical, low temp. Plus, it's rated to 45 bar suction and 60 bar discharge. So a little bit different. There's a trend in Europe for higher standstill pressures on the low temp side and the medium temp. And it's one of these things that are addressing these higher standstill pressure requirements. And the ZOV meets those requirements.
Awesome. So inside, there must be different components inside the ZOV compared to the ZO. For example, I know in the HFC one, there was a pump inside those ones. What other components in this is there? Would there be that pump inside this compressor?
When you start varying the speed so much, there's special design requirements that change. Instead of just some of them have positive displacement pumps
Mm-hmm.
and others don't. So
Okay.
when you've got a compressor that has such a wide range, you've got to make sure that whatever design you implement is got to be able to pump that oil at 20 hertz
Yeah.
that we talked about. That you need that as well as 100 hertz. You don't want too much pumped as well, right? Because it's going so fast. So you've got to find that balance to have the right oil distribution system for those that range.
Yeah. Yeah.
Absolutely.
So why would someone pick, say, for the low temp side, why would someone pick a semi-hermetic or a scroll over one or the other? What are some of the things that you've seen with customers purchasing the low temp side? Because now you got two options, right? You got the semi-hermetic, you got the scroll. Why would you pick one over the other?
Well, it depends what you're talking about. If you're talking about high standstill pressure versus lower standstill pressure,
Mm,
that's a requirement. If you're looking at cost. Sometimes cost is a requirement to pick one technology versus another. Sometimes it's weight. Sometimes it's size of footprint. So, the scroll is half the weight of a typical semi-hermetic.
Wow.
That's one thing.
Yeah.
It does have the modulation range down to 10%. So that's another. So if you're looking for wide range of modulation down to that 10%, and you're looking for a lighter compressor and footprint size on your rack, so it doesn't take up as much width. Yeah, it'll take up more height, but not as much width. Then you may want to look at the scrolls over a semi-hermetic. Now, if you're looking for a system that will have high standstill pressure when the pressures are off, let's say 60 bar or 90 bar, well, the scroll is not rated that high. So you're going to go to a semi-hermetic like a 4MSL that I talked about earlier, that has 135 bar standstill, way higher than you're going to need for low temp, but you've got that high standstill pressure resiliency.
Yeah.
And that's important. That might be important to one customer,
Yeah.
from their specification perspective.
Yeah, and that's very important, because I see the industry going more and more that direction. I see more, even over the last 6-7 years, I see more components being able to do 120 bar, 130 bar, and I believe that's going to be a consistent trend. And then as we develop more components and the prices come down, and there's more in the market, more price competitive, we'll see more and more systems that I believe that'll have a standstill pressure where it can just shut it off and you're not blowing reliefs.
No, you're right. I mean, the industrial side of the business is leaning towards that already, because they don't want to have these large generators, to keep the system running, or have an auxiliary condensing unit when the power goes off to just cool the flash tank, to keep the pressures in the flash tank and liquid line low. If they don't want to do that, then they have to design the entire system, including the low side, to higher resiliency, higher standstill pressures, so that when it's off, it's off. It's just like condensing unit designs that, a condensing unit doesn't run 24/7. Maybe it's for a production or whatever, and it'll be off for a day or two or over the weekend.
Yeah.
So that system, if it's CO2, either is going to need to have an auxiliary unit to keep the pressures low, or the whole unit will need to be built to a higher standstill pressure. So when it's off, no wait, no headaches. It can manage those pressures without blowing a CO2 charge.
Yeah. And that's important to understand. You got to work with your customer. You got to understand the system you are working on. So I know Copeland's in Europe is in the development of transcritical scrolls, and I know there'll be many, many years before they're mainstream. Can you talk a little bit about what's going on with the development of those scrolls?
Sure. So last September, our European colleagues did launch a what's called a transcritical scroll. And you just mentioned 130 bar. I mean, that the shell is rated to 140 bar.
Wow.
For example. It's rated to operate at 120 bar, so that's 1,720 pounds operating. Wow. It has a, excuse me, it has a variable speed range, 25 to 90 hertz. I believe it's 25 to 90 hertz. It's no higher than 90 hertz, excuse me. So that's another peculiarity.
Yeah.
And if you're familiar with our vapor injected HFC scrolls, our ZF KVEs, okay? We took that vapor injected philosophy and applied it to CO2 transcritical scrolls.
Ooh.
So now it has vapor injection.
Wow.
And say, where do you get the vapor from? Well, if you look at the image on the screen now, if you're just listening to a podcast, let me talk through it, because one of the high ambient strategies with CO2 systems, in order to get better efficiencies in warmer climate, is to add a compressor that's called a parallel compressor. And that compressor even though it discharges into the same gas cooler, its suction vapor comes from the flash tank. So that parallel compressor digests the excessive flash gas in the flash tank, and instead of sending it to the medium temp suction, it sends it to a parallel compressor to improve efficiency.
Yeah.
And depending on where you are in the world, that can range from 8 to 10, 11%. And we've shown that in our climate study that we've just completed on CO2. But what this transcritical scroll does is, because it's vapor injected, it takes that excess flash gas from the flash tank, and instead of sending it to the medium temp suction, which is inefficient, the EVI digests it. So that flash gas vapor gets sent into midway into the compression cycle of the scroll. Just
Wow.
like it does on a HFC EVI type, the same type of concept from an injection perspective. And what that does now is it gives you a small footprint, higher efficiencies, without the added complexity of another suction group on your medium temp, which would be called the parallel compressor. So we can eliminate that parallel compressor, but get the same efficiencies out of the transcritical scroll. So we're pretty excited about that.
Yeah.
And there's two types of architectures you could use. I mean, you can also float your flash tank, which is something we don't do on typical booster systems, but with this technology, you can literally float your flash tank up to 60 bar and down to 35 bar, depending how warm or how cold it is. And that pressure will just continuously be digested through the DVI port. It's called dynamic vapor injection.
Well, that's impressive. So when you're able to do that with your flash tank, would that be similar to something like floating suction on a standard rack to get more efficiency out of the system?
It's a means of getting more efficiencies at higher temperatures. Right, but it's not done on the suction side.
Okay, yeah, you're right.
Right. So yeah, then that's good parallel.
Yeah, no, that's really impressive. I'm excited to see some of those. I know it's going to be a while. It's new technology, but I'm excited to see that. Are you seeing more manufacturers building CO2 condensing units? Because I know in Europe they've had Emerson had a CO2 condensing unit for years and years and years now. Are you seeing more of that play happening in the industry?
Yes, it's starting. It's starting here in North America. Of course, Europe has been ahead of us because of a number of reasons. They've started CO2 10 years before North America, pretty much. There's a lot of countries that have incentivized condensing unit use, so that really helps to defer the cost of condensing units. So that's important. In North America now, our OEMs are being asked for these condensing units. So development has started. So that's encouraging. And also you're going to start to see a lot more distributed booster systems here in North America. We've seen advertising of them in Europe as well. But now, because of the smaller footprint compressors as well, end users are saying, well, instead of having one large centralized plant, can I maybe have 2 or 3 of these systems spread out throughout my store, like I did in the past, maybe with HFC systems? And that could be part of a remodel strategy. Instead of rip and replace everything, then you can carve out a portion of your store, not have too much customer disruption, and focus on that section, and then move on as time goes on or as budget permits or whatever. But eventually you're moving into a natural refrigerant on a phased perspective.
Yeah. And I've seen that. I've worked at Targets before where they had like 3 or 4 different porta packs or protocols across because they're big stores.
Right.
I've seen them maybe at Walmart's as well. And I think that way will continue to grow, because instead of running a 4-in-1 pipe, I remember running them from the back of the store all the way to the front, hundreds of feet. You'd have a
Yeah.
lot smaller pipe, more central, more like that section of it would be more centralized to that one area.
Yeah.
So pretty cool. I like learning these different ways of doing it. It's nice to see that, because that is different than what it was done before, really.
Well, it's a mindset that we have in the commercial refrigeration. Some customers like that architecture style. You can optimize your suction pressures too. You know,
Hmm.
you're not stuck to that lowest medium temp suction that your whole system has to sacrifice to, right? So you can carve those out, and because a lot of these retailers are looking at not just naturals, but they have to start thinking more along, I got to make these systems as energy efficient as possible, because if they're going to start to report their scope 2 emissions and start working towards their net zero carbon emission goals of 2030 that a lot of them have, energy is the biggest component.
Mm.
So those steps have to start now to get ready to meet those net zero targets.
Yeah. Yeah, and that makes sense, right? Because there's a lot of regulations. And this is what I tell technicians: you need to be at least in the know of what's going on with refrigerants. Because I still talk to contractors; they're still installing 404 systems, and that's
Yep.
been illegal here in Canada for many years now. You can't be
Yeah.
doing that. Yes, you can use it for service, but new installs, it's not legal to do that. And I didn't know. Nobody's mentioned this to me. You know what I
Yeah.
mean? And they're
Yeah.
sending me the equipment that has 404. They're sending the trucks with the 404. So this is something that you need to be aware of as a refrigeration professional yourself. So understand that stuff.
Absolutely. No, absolutely. And try to guide your customers into another option, because, in 2024, when production drops by, it'll be at 60% of the 2011, 2013 number.
Hmm.
So there's going to be a big drop in 2024. That means the price of those high GWP refrigerants are going to go up. We've seen
Yeah.
it in other parts of the world, so we know it's going to happen here.
Yeah.
So try to protect your customer against those costs.
Yeah.
You know,
Yeah, no, exactly. And that's just being aware of what's going on. And because there's so much going on in the refrigeration industry with CO2 and with regulations. And that's why we're seeing more and more CO2 or natural refrigerants coming out. What else would you like to add for the compressor side of things, Andre?
um, the only, I guess, the only other thing is, from a compression perspective, from in order to be able to run them effectively, is the drives that we've launched this year.
Okay.
The Copeland drives that have been integrated, of course, into our controls, and of course made set up to be optimized to run with the 4 MTLSs. So we're pretty happy about that. The drive we've got from 5 to 25 horse is called the micro drive,
Okay.
and the other ones goes up to 250 horse. EVM, micro, and EVH is our other drive. So we're pretty happy about the launch of those products.
So what would be the difference than just taking a standard Danfoss and putting it on it compared to one of these drives? Is there less parameters? Is it just plug and play? Like how does it make it any different than using like the popular drives that are out there today?
Yeah, one of the things that the drives have in them, they've got a 200% overcurrent protection for 2 seconds. So you don't have to oversize the drive as much for those overcurrent conditions that happen. And that can happen 20 times in a minute for 2 seconds each.
Wow.
So that's a kind of protection. So from a sizing perspective, that's one thing. The other thing that we're working on and getting very close to is, because we've got Copeland mobile app, that you can find all kinds of compressor information. But not only that, it'll be super easy to size the drive per the compressor and be able to push the values into it,
Mm.
because it'll all be tracked in Copeland mobile. We're not quite there yet, but that's the goal of that whole integration of compressor ease of use, ease of parameter setting, and then push that up into the E2 because it's been mapped. So we're pretty excited about working through all that to simplify all of that, the work involved in drives
Yeah, and I like
and
that because
setting them up.
I've sized lots of drives, and I've talked to lots of people how they size drives, and lots of people size them differently. So,
Right.
some are oversized, some are borderline, and it's important that if we can make it easier for people out
Right.
there, and it doesn't matter how you're doing it, you want to get the right stuff in there because it causes problems down. It can cause problems down the road, especially if you get the
Right.
wrong size drive. So, any way to make it easier.
Absolutely. Absolutely.
Um,
That was a great point.
And I see on the screen there, I know we were talking about compressors today. You got the E3 CO2 controller, and I see it says CO2. Can you just, we only got a few minutes here. Do you want to
Sure.
elaborate or talk about that a little bit?
Yeah, I'm thrilled about this product because it's something that it's kind of near and dear to my heart to have, as you know, working for Emerson at the back in the day, is having CO2 applications
Mm,
in a rack control. And that's what this thing does now. As part of the CO2 suction group, you order a standard E3, but you order a license for the CO2 applications that'll have embedded CO2 applications in there as part of the suction group. We already control adiabatic gas coolers, but to have the application set for parallel compression, for example, you don't have to write a flex combiner or a little
awesome.
macro to do that.
Yes.
The liquid injection, the hot gas dump injection, heat reclaim, mechanical subcooling, those are all going to be half of those are native already, and we're working on the other half. The mechanical subcooling we're working on, and eventually we'll layer in ejector management as well. So to have those native applications in there are going to be, well, they already are awesome because we've got them out and running. You've
Awesome.
got startup, the standard startup sequence to make sure that the right percentage of loads come on, low temp and medium temp, not to overload the system. That's native. Also shutdown sequence, that's native. So there's a lot of new features that we're thrilled about.
Yeah, no, that is super important. Those few things, because I know working with contractors, having to build that in there, that's a big job, right? When you have to build flex complainers and you're building these programs yourself to make sure that store, if something happens, that it shuts down and starts up properly, because
Right.
you could blow the whole charge on on startup very easily. So
Right.
having that native is very, very important.
And the other thing too, Trevor, is the fact that this processing speed is much higher than the E2. So for
Mm,
CO2, we all know that CO2 pressures and temperatures change very, very quickly. And
mhm.
that's why it's all electronic. That's why it's all got electronic valves because of that. So we've got a processor that's much faster. And, not just that, you can pull all of those extra peripheries into one dashboard. Either you have it on the device at the rack, and you can set it up the way you want to look at it, or you can do it on your phone, your tablet, or your PC now. So it's completely mobile access. So that's a really cool feature.
Yeah, that does sound like it. I'm excited to see some of those, and I know that I've talked to a few people starting to see more and more of them out there. It's even better to see that they have them for CO2 applications, which is great.
Yeah. Yeah, the CO2 Transcritical mobile trainer in the US and Canada will be retrofitted to that in the next
Awesome.
few months through the summer. So it's ready for the educational season in September, October.
That's
So I'm
fantastic.
happy about that.
Yeah, that is great. Any final thoughts on Copeland CO2 compressors? Or
No, not
yeah,
that I could think of right
yeah,
now. I think we did a good job of plugging me along to ask and get some questions.
yeah, no. I think it's so important to get into those application engineering bulletins. Whatever compressor component you're working on CO2, understand how it works, how to install it, how to set it up, how to maintenance it, how to troubleshoot it. It's very, very important, especially with CO2. It's still new. You know, it's been out for 20, to 20 years, and well, even longer than 20 years. CO2 has been out forever, but all these new
Right.
components, understand them. So if people want to get a hold of you, Andre, or get a hold of Emerson, how would they do that?
Oh, they can reach me at my first name, Andre, Andre, dot, my last name, Patenaude, Patenaude, Naude at emerson.com.
Awesome. Awesome.
Yeah.
So we'll go into some questions here. See if anyone has any questions. You can unmute yourself because this is a live event, or you can shoot it in the question or in the chat. We've got 5 minutes left, so we'll sit here and see if anyone has any questions. There was one in the thing here. Minimum speed, I guess, for variable speed, also for oil return to the compressor. Yeah. So I know on variable speed compressors, a lot of times they'll do oil bump cycles. So depending if you're running at a minimum speed for so long, maybe 2 hours, depending what it is, it will boost it back up to say 60 hertz and just get that
Right.
oil running maybe 5 minutes. But that's sometimes set up in the drive. Sometimes you have to set up yourself. I'm assuming with these new drives, that'll be already set up.
Well, there's that, but on a single condensing unit type scenario, that's something you need to worry about. On a booster rack where you're pulling oil off an oil reservoir, a little bit different situation. So because you've got the track soil on there, opening and closing, even if it may not be that specific compressor may not be drawing as much back, but the entire system is separating it and returning it properly.
Yeah, no, that makes sense. All good things to understand when you're working on those systems.
Sure. While you're reading there, I could tell you, we talked about the one main lab, a large supermarket lab, but there's another 3 labs going on in Ohio, all around CO2. One is a transcritical scroll lab, and 2 others are on condensing units. So you asked about condensing unit. Even though Emerson, we're not building a condensing unit for CO2 in North America, our European colleagues have one, but we're not. We're building them in our own Sydney lab facility so we can support our OEMs.
Wow.
And those will all be up and running in the next month or 2. There's a lot of labs coming on stream this summer.
Wow.
There'll be actually 4 CO2 labs in all. So a lot of development going on for sure.
And so how would that work? So you'd work with your partners, your OEM partners, and they would say, okay, I would like to test this in your facility with your compressors, I guess, or components, whatever. And you guys would do like all the specifications, see how it runs, see like the testing of it, what works, what doesn't work, operation envelopes, things like that.
That's part of it. The other OEMs like to do it in their own labs as well. So they're going to run some tests, but we can simultaneously run similar tests, understanding, functions of the controller operating at different points that maybe they don't have access to in their labs because their equipment is limited to X, Y, or Z. Run that point, we can run the others, and that kind of collaborative back and forth to try to get a product to market much sooner.
Awesome. That is awesome. Well, Andre, thank you so much for your time today. I really appreciate you. I really appreciate this. And I can't wait to see all of you at the next CO2 Mondays with Trevor. Have a great day.
Great. Take care.